Right now, without you knowing it, our entire galaxy is being dragged through space at nearly 1,400,000 miles per hour, not drifting, not wandering, being pulled. Something massive is hiding behind the Milky Way, something so large, so powerful, that every galaxy within hundreds of millions of light years is moving toward it. And here is the terrifying part: we cannot see it directly. Our own galaxy is blocking the view. We are about to travel into the Zone of Avoidance, past the hidden superstructures buried in the darkness, and face the most powerful gravitational force humanity has ever tried to understand. You are going to discover galaxies hidden behind our own. You will meet the Great Attractor, a structure so dense it bends the path of our cosmic neighborhood. You will learn why astronomers call one region of space forbidden, and you will find out why some scientists believe something even bigger may be hiding beyond all of it. If this sounds like the kind of video that keeps you up at night, hit like and subscribe. You are going to want more of this. Take a breath. We are heading into the deep. There is a band of sky that astronomers, for most of history, refuse to trust. It runs like a scar across the entire night sky, stretching from one horizon to the other. No stars stand out there as landmarks. Telescopes pointed toward it returned blurry, distorted images. Signals got swallowed. Galaxies that should have been visible simply vanished. This band is called the Zone of Avoidance, and it exists because of our own galaxy. The Milky Way is not just the glowing river you see on a clear night in a dark field. It is a flat disk of billions of stars, gas clouds, and dust, and we are sitting inside it. When we look outward toward the edges of the universe, most directions are clear. But when we look toward the center of our own galaxy, or along its flat plane, we are staring through hundreds of thousands of light years of dense, dusty material. That dust is not like the fine particles floating through your room in sunlight. In space, dust is made of carbon, silicates, and frozen molecules that block visible light the way a brick wall blocks your hand. Entire galaxies sitting just on the other side become invisible to optical telescopes. Whole clusters of stars, the size of cities of light, are swallowed whole. For early astronomers, this was simply the edge of the known universe. They assumed there was nothing there, but that assumption was one of the most consequential mistakes in the history of science. By the mid-1900s, astronomers began noticing something strange. When they mapped all the galaxies they could detect, they kept finding a pattern. Galaxies were not spread randomly through space. They were moving, flowing, and all that flow seemed to point toward a single direction, a direction that sat suspiciously close to the Zone of Avoidance. Something was pulling them, something hidden behind the one wall they could not see through. Think of it like standing in a city where a massive mountain is hidden behind heavy fog. You cannot see the mountain, but every road, every river, every wind current seems to angle toward it. Over time, that invisible shape reveals itself not through sight, but through everything else it affects. That is what the Zone of Avoidance did to astronomers. It forced them to chase shadows and feel out the shape of something they were not allowed to directly observe. Scientists began calling the source of this gravitational pull the Great Attractor, a name that sounds dramatic because it is. But before they could understand what the attractor was, they needed a way to pierce the veil. Early radio telescopes helped a little. Radio waves pass through dust better than visible light, the same way radio signals travel through walls that stop sound. But radio mapping of that region was slow, incomplete, and uncertain. Then, in the 1980s, a team of astronomers developed a new way of counting galaxies behind the dust. They used infrared light, which passes through galactic dust more easily than visible wavelengths. Suddenly, the fog started to thin. What they found hiding behind the Milky Way was not a quiet, empty region of space. It was a crowded, violent, breathtaking universe that had been invisible to us the whole time. And somewhere inside it, something was waiting. something with enough gravitational muscle to drag 100,000 galaxies across millions of light years, like pulling a rope through water. What that thing actually is, and how much bigger it might be than anyone first assumed, is where this story is about to get far stranger. The people who first tried to map the zone of avoidance were working almost blind. In the early 1900s, astronomers had no infrared detectors, no X-ray telescopes, no computers to crunch millions of data points overnight. They had photographic plates, pencil marks, and arguments that could last decades. One of the first serious attempts to understand what lay behind the galactic plane came from an astronomer named Harlow Shapley. In the 1920s, Shapley was trying to map the entire Milky Way, and in doing so, he kept running into the same problem. Near the plane of the galaxy, the star count dropped suddenly, not because stars stopped existing, but because dust was absorbing their light before it reached his telescope. Shapley called this region the Zone of Avoidance for the first time, and the name stuck. He did not know what was hiding there. He simply knew he could not get a clear answer, and honest scientists admit when the data stops being trustworthy. But Shapley noticed something else. A strange concentration of galaxies seemed to gather just beyond the forbidden zone in the constellation of Centaurus. He called this gathering the Shapley concentration, though even he could not be sure of its true size or distance. He was mapping coastlines from a boat in fog. Decades passed, telescopes improved, but the zone remained resistant. Then, in the 1960s, radio astronomy changed everything. Radio waves travel straight through interstellar dust, the way light travels through clear glass. Telescopes designed to receive radio signals started detecting hydrogen gas on the far side of the Milky Way, in regions where optical astronomers saw nothing but blackness. Early radio maps were crude, like drawing a continent based on a few coastal signals and guessing the interior. But they confirmed something important. Galaxies existed behind the zone, many of them, possibly more than anyone expected. By the 1970s, the first serious radio galaxy surveys of the Zone of Avoidance were underway. Astronomers at Parkes Observatory in Australia swept the sky with a dish the size of a football field, listening for the faint hum of hydrogen 21-centimeter radiation, which galaxies emit naturally. They found galaxies, hundreds of them, hidden right in the shadow of our own home, and they found something troubling. The distribution of these galaxies was not uniform. They were not scattered randomly. They were clustering, gathering, pulling towards certain points like iron filings toward a magnet. This was the first real whisper of the Great Attractor. Not an image, not a confirmed structure, just a gravitational imbalance, a tilt in the universe around us that pointed towards something enormous in the direction of Centaurus and Norma. One of the key teams working on this problem was a group nicknamed the Seven Samurai, a collaboration of 7 astronomers who, in the late 1980s, used the motions of elliptical galaxies as measuring tools. By tracking how fast galaxies were moving and in which direction, they could trace the gravitational landscape behind the zone. Their conclusion was stunning. There was a concentrated mass, somewhere around 250 million light-years away, in the direction of the Zone of Avoidance, powerful enough to affect the motion of the entire local universe. The Great Attractor was not a theory anymore. It was a measurement. What exactly made up that mass, however, was still unknown, and the search to answer that question would lead to discoveries far bigger than any of them had imagined. The breakthrough came not from a bigger telescope, but from a smarter kind of light. Infrared radiation sits just below visible red light on the spectrum. Your body emits it constantly as heat. Remote controls use it to change channels. But for astronomers, infrared is a key that opens doors no visible light telescope can unlock. Dust in the Milky Way blocks visible light almost completely in certain directions. But infrared passes through that dust the way a strong radio signal passes through a concrete wall. The dust still dims the signal somewhat, but it does not erase it the way it erases visible light. In the early 1980s, A satellite called the Infrared Astronomical Satellite was launched by a collaboration of American, British, and Dutch space agencies. It mapped the entire sky in infrared for the first time, and when astronomers pointed its data toward the Zone of Avoidance, the results were historic. Galaxies appeared. Not a few, not dozens. Thousands of galaxies materialized in infrared maps that showed nothing in visible light. The hidden universe behind our own galaxy was enormous, crowded, and structured. But IRAS, as the satellite was called, had limitations. Its resolution was low, and its sensitivity was designed for nearby objects. The galaxies it detected were confirmed real, but the fine structure behind them remained fuzzy. The real turning point came with ground-based infrared surveys in the 1990s. Teams at Leiden Observatory and later at Harvard-Smithsonian used improved infrared detectors on ground telescopes to conduct the 2-micron all-sky survey, which became known as 2MASS. This survey mapped the entire sky in near-infrared with sensitivity and resolution that made the earlier work look like sketches compared to photographs. 2MASS penetrated about 87% of the zone of avoidance that had been completely opaque to visible light astronomers. In the deepest and most obscured 10%, other techniques were needed, but for the vast majority of the zone, the veil had lifted. What appeared in those maps was a universe of staggering scale. Behind the Milky Way, in the direction of the constellation Norma, astronomers confirmed the existence of a massive cluster of galaxies. Thousands of galaxies bound together by gravity into a structure larger than any city we could possibly imagine. This was the Norma cluster, and it sat almost exactly at the position where the gravitational calculations said the Great Attractor should be centered. The Norma cluster alone contains more mass than most humans can picture. A single galaxy, like our own Milky Way, has around 200 billion stars. The Norma cluster holds thousands of galaxies pressed together, their gas and dark matter halos overlapping, their combined gravitational pull stretching across tens of millions of light-years. But here was the part that made the room go quiet. Even the Norma cluster, massive as it was, could not fully explain the motion being observed across the local universe. The gravitational pull pointing in that direction was too strong, too broad. Something larger had to be contributing. Think of it this way. If you threw a bowling ball into a lake, you would see ripples spreading outward. But if the ripples were too large, too powerful for a single bowling ball to explain, you would have to consider that something heavier was thrown in somewhere nearby. The universe was showing ripples no single cluster could produce. Something bigger was waiting to be found. The Norma cluster is not a peaceful place. At the center of the hidden region astronomers call the Great Attractor, where thousands of galaxies press toward each other under enormous gravitational force. The Norma cluster sits like a beating heart. And like a heart, it is not still. Galaxies inside the Norma cluster are colliding, merging, and tearing each other apart. When two galaxies meet at the speeds found in a dense cluster, they do not pass through each other cleanly. Stars are flung into new orbits. Gas clouds collide at millions of miles per hour, heating to temperatures that emit X-rays. Entire spiral structures are stretched and distorted into smooth elliptical shapes by the tidal forces pulling at them from all sides. The Norma cluster is formally catalogued as a mass of galaxy clusters at a distance of roughly 220 million light-years from us. That distance is so immense that even light, moving at nearly 300,000 kilometers per second, takes 220 million years to cross it. To put that in a way that means something, the light you would see from Norma left that cluster before the dinosaurs existed, before complex animal life on Earth had developed eyes, before any organism on our planet had evolved a nervous system. That ancient light is only now reaching us. And yet, despite that distance, the gravitational pull of what lies in that direction is strong enough to deflect our entire galaxy from where it would otherwise be traveling. That is the scale of what we are dealing with. Inside the Norma cluster, the brightest galaxy, called Norma Galaxy Cluster's dominant member, or informally ESO 137, has been studied in extraordinary detail using X-ray telescopes. What they found there is one of the most visually striking phenomena in astronomy. As this galaxy moves through the hot gas filling the cluster, it leaves behind a glowing blue trail of ionized material being stripped from its spiral arms. A comet tail made of young stars being ripped loose and dragged behind their galaxy like a banner in a hurricane. This process is called ram pressure stripping, and it happens when a galaxy moves fast enough through a gas-filled medium that the pressure tears away the galaxy's own gas before new stars can form from it. The galaxy is slowly being starved of the fuel it needs to keep building itself. It is an extraordinary image, a galaxy losing pieces of itself as it falls, like a spacecraft shedding tiles on re-entry. But the Norma cluster is only part of the story. Its mass is real and enormous, but astronomers in the early 2000s ran the numbers again using updated data from larger surveys and more sensitive instruments. The conclusion was unsettling. Even with the Norma cluster fully accounted for, the gravitational acceleration of our local universe still could not be fully explained. The tug was too strong. The flow was too broad. Norma was a major landmark, but not the whole source. The search expanded outward, beyond Norma, deeper into the zone of avoidance and the regions just beyond it. What they found there, buried further behind the dust and sitting at even greater distances, changed the map of the local universe in ways that are still being absorbed into our understanding of cosmology. Something even more massive was lurking deeper in the dark. The name Great Attractor sounds like something from a science fiction story. It is not. It is a scientific measurement, a calculated center of gravitational pull toward which our entire galaxy, along with every other galaxy in our local neighborhood, is currently moving. Not slowly, not gradually over billions of years. Right now, at speeds that would leave you speechless if you converted them into something human-scaled. Our Milky Way is falling toward the Great Attractor at roughly 1 million miles per hour relative to the background radiation of the universe. Everything around us, the Andromeda Galaxy, the galaxies of the local group, the nearby Virgo cluster, all of it is flowing in the same direction, dragged by the same enormous gravitational force. For decades, astronomers referred to the Great Attractor as a zone, not a single object, because no single object is responsible. The gravitational pull comes from an accumulation of mass across tens of millions of light years, concentrated in the direction of the constellations Centaurus and Norma. The Norma cluster forms one anchor of this mass concentration, but the larger structure includes clusters, superclusters, filaments of dark matter, and gas spread across an enormous volume. In the 1990s and early 2000s, deeper X-ray surveys and updated galaxy redshift catalogues allowed astronomers to finally build a three-dimensional map of the mass in that region. The picture that emerged was of a supercluster, a collection of galaxy clusters gravitationally connected and flowing toward a common center. This supercluster, which includes the Norma cluster and its surroundings, represents a density of matter perhaps 10,000 times greater than the average density of the universe around it. Think about that. In most directions, space is almost unimaginably empty. The average distance between galaxies is millions of light years, but in the direction of the Great Attractor, matter is packed in at a density that compresses what should be spread across vast distances into a concentrated knot of gravitational force. There was a period around the early 2000s when some astronomers believed the Great Attractor mystery had been largely solved. They pointed to the Norma cluster and the surrounding supercluster and said, "There it is. That is what is pulling us." But then new data started coming in. A survey completed in 2014 used a large network of radio telescopes to map galaxies in the zone of avoidance using the 21 centimeter hydrogen line signal. This technique revealed something hiding even deeper in the shadow of the Milky Way, at a distance further than the Great Attractor, in a region that had not been fully explored. What they found was the Vela Supercluster. It had been invisible, hidden behind the thickest part of the dust, sitting behind a part of the zone even infrared surveys struggled with, a structure as massive as the Great Attractor itself, sitting at roughly 800 million light-years away, contributing its own pull to the gravitational landscape of the local universe. The Great Attractor was not the only giant, and behind it, even further still, something even larger was casting an even longer shadow. The universe was doing what it does best. Just when we thought we had measured it, it showed us how little of it we had actually seen. Imagine standing on a boat in the middle of a river. The current is invisible to you. There is no smell, no sound, no sensation to tell you the water is moving. But the boat drifts. Slowly, steadily, it moves in one direction, and no amount of reasoning about the boat itself explains why. That is the situation our galaxy is in. From inside the Milky Way, you cannot feel the motion. You cannot look out a window and watch the universe scroll past. But astronomers can measure it precisely by comparing the motion of our galaxy against the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire universe almost uniformly. When they do that measurement, the results are extraordinary. Our galaxy is not just drifting. It is participating in a massive flow of matter through the local universe, moving at speeds that only make sense when you account for the gravitational pull of enormous structures in specific directions. This flow is called a peculiar velocity flow, meaning it is a motion that exists on top of the general expansion of the universe. As the universe expands, all distant galaxies move away from us, carried along by the stretching of space itself. But peculiar velocity flows are different. They represent the additional motion galaxies experience because of gravity, because the universe is not evenly distributed, because some regions are denser than others. The peculiar velocity flow in our cosmic neighborhood is one of the largest such flows ever measured. It involves thousands of galaxies all streaming in broadly the same direction, like tributaries feeding into a cosmic river. At the center of this flow sits the Great Attractor region, but it is not pulling alone. In 2017, a team of astronomers published a landmark study mapping the peculiar velocity flows of over 8,000 galaxies across a volume of space spanning hundreds of millions of light-years. What they found was a dual structure of cosmic forces. On one side, the Great Attractor and its surrounding superclusters were pulling our local universe toward them. On the other side, a vast underdense region called the dipole repeller was pushing matter away from itself, effectively shoving our galaxy toward the attractor, the same way a void in a river creates a current toward denser water nearby. Our galaxy's motion is therefore the result of two forces acting in coordination: a massive gravitational pull from the direction of Norma and Centaurus, and a gravitational push from an enormous cosmic void in the opposite direction. You are living on a planet inside a solar system, inside a galaxy, being both pulled and pushed across a river of space at more than 1 million miles per hour, and you cannot feel any of it. The sheer scale of these structures puts the human mind in an uncomfortable place. The attractor region spans several hundred million light-years. The void behind us spans a comparable distance in the other direction. These are not features on a star chart. They are structural elements of the universe itself, and every galaxy in our local group, from the Milky Way to Andromeda to dozens of smaller satellite galaxies, is caught in this flow. None of it will slow down anytime soon. The river has been running for billions of years, and the largest rapids are still ahead. For most of the 20th century, it was invisible, not hidden in a subtle way, completely, utterly invisible to every telescope pointed at that region of the sky. Because the Vela Supercluster sits behind the thickest part of the Zone of Avoidance, in the portion of the galactic plane where dust is so dense that even infrared surveys struggle to penetrate. The first strong hint that something enormous was hiding there came in the 1980s, when astronomers noticed a statistical anomaly in galaxy counts near the southern Milky Way. There seemed to be a slight overdensity, a cluster of signals above the noise level, but the data was too sparse to draw conclusions. It was filed away as a curiosity. Then, in 2014, an international team led by astronomer René Kraan-Korteweg conducted a deep survey using the Parkes radio telescope in Australia, scanning the zone of avoidance with extreme sensitivity. They were looking for the 21-centimeter hydrogen line emission from galaxies, the faint radio signal that hydrogen gas emits naturally and that travels through galactic dust almost unimpeded. What they found stopped the room. Tucked behind the zone of avoidance, at a distance of approximately 800 million light-years, was a massive concentration of galaxies. Not a cluster, not a small supercluster. A structure containing thousands of galaxies, spread across a volume of space roughly 300 million light-years wide. They named it the Vela Supercluster. Its mass is estimated at around 1,000 times the mass of the Milky Way in galaxy clusters alone, not counting dark matter, not counting the filamentary gas connecting its constituent parts. The discovery was published in 2017 and caused immediate recalculations. Astronomers had previously assumed they understood the gravitational forces acting on the local universe well enough to account for the observed peculiar velocity flows. The Vela Supercluster, sitting at twice the distance of the Great Attractor, broke those calculations wide open. At 800 million light-years away, the Vela Supercluster is far enough that its individual gravitational pull on our galaxy is weaker than the Great Attractor's direct tug. But that is not the right way to think about it. What matters is the large-scale flow of matter through an enormous volume. When a structure as massive as Vela sits in one direction and pulls on everything within its gravitational reach, it accelerates not just our galaxy but thousands of other galaxies and clusters toward itself. That acceleration adds to the overall motion of the local universe, bending the flow of matter across hundreds of millions of light-years. Vela is a second engine in the gravitational machinery driving our cosmic neighborhood, and here is the detail that kept some astronomers awake at night after the discovery was announced. If a structure the size of the Vela Supercluster was sitting undetected behind our own galaxy until 2017, what else might still be hiding in that band of forbidden sky? The zone of avoidance covers roughly 20% of the visible sky. Even with radio surveys and infrared maps, the densest regions remain difficult to probe. In those remaining shadowed strips, entire superclusters could be lurking, completely unrecorded in any catalogue, pulling at the local universe without any human ever having noticed. The universe had been keeping secrets from us for a very long time. In 2014, something changed about the way we understood where we live. Not on Earth, not in the solar system, not even in the Milky Way. The change was at a larger scale than any of those, a scale so large that the word home takes on a meaning your brain will struggle to contain. A team of astronomers led by Brent Tooley at the University of Hawaii published a study that redefined the supercluster our galaxy belongs to. Using a massive three-dimensional map of galaxy velocities across the local universe, they traced the watershed boundaries of gravitational flow. Just as water flows across a landscape and collects in valleys and basins, matter in the universe flows under gravity and gathers into basins of attraction. By mapping where the flow boundaries were, the team identified a single enormous basin of attraction, a region of the universe where all matter is gravitationally bound and flowing toward a common attractor point. They called it Laniakea. The name comes from the Hawaiian language and translates roughly to immeasurable heaven. It spans 500 million light-years across. It contains the mass of approximately 100 million billion stars spread across 100,000 galaxies. Our Milky Way sits near the outer edge of Laniakea, in a smaller cluster called the Local Group, which itself sits on the fringes of a larger structure called the Virgo Supercluster. We are in the suburbs of a cosmic metropolis, the heart of Laniakea. The center toward which all matter inside it is flowing is the Great Attractor region. Specifically, the Norma cluster and its surrounding mass concentration. This means that our galaxy is not simply near the Great Attractor by coincidence. We are gravitationally part of the same structure. We belong to Laniakea, the way a single raindrop belongs to the Mississippi River watershed. Eventually, on timescales of billions of years, matter in our region of Laniakea will flow toward the core. But here is where the story adds a layer of cosmic irony. The universe is also expanding, and its expansion, driven by dark energy, is accelerating. On the scales of hundreds of millions of light years, the expansion of the universe is pulling galaxies apart faster than gravity can draw them together. This means Laniakea is being torn apart from the outside even as it contracts from the inside. The galaxies at Laniakea's edges, including our own Milky Way, are being tugged outward by the expansion of the universe and inward by the gravity of the supercluster simultaneously. The outcome of this tension is uncertain. Some models suggest our galaxy will eventually fall into the deeper gravitational core of the local universe. Others suggest the expansion will win, and Laniakea's members will scatter. Either way, the identification of Laniakea was a landmark in human understanding. For the first time, we had a name and a shape for the largest structure we belong to. We had drawn the coastline of our cosmic continent. And on that continent, the Great Attractor sits at the center, and hidden behind the dust, behind the Zone of Avoidance, behind the veil our own galaxy throws across the sky, something is still pulling everything in that direction. Something we may not have fully found yet. When the Great Attractor was first described, astronomers assumed it was the main engine driving the motion of the local universe. They were wrong, or rather, they were only partially right. Behind the Great Attractor, in the same general direction but twice as far away, sits the Shapley Supercluster. And it is not just big, it is one of the most massive gravitationally bound structures in the observable universe. The Shapley Supercluster sits at a distance of approximately 650 million light-years. It contains over 30 galaxy clusters, more than 8,000 individual galaxies in its densest parts, and a total mass that exceeds 10 million billion times the mass of our own galaxy. To appreciate that number, consider this. Our galaxy has an estimated 400 billion stars. The Shapley Supercluster has a combined stellar mass equivalent to roughly 10 million Milky Ways, plus the dark matter halos that surround each of those galaxies, plus the hot gas threading the space between them. This is not a structure that sits quietly in the background. Its gravitational influence extends across hundreds of millions of light years and contributes significantly to the overall flow of our local universe toward that region of the sky. In fact, recent studies using improved peculiar velocity surveys suggest that the Shapley Supercluster may be responsible for approximately as much of our galaxy's peculiar velocity as the Great Attractor itself. The two structures work together, like two anchor points on the same gravitational rope, pulling the local universe toward the southern sky. Harlow Shapley, the astronomer who named the Zone of Avoidance and noticed the concentration of galaxies in that direction nearly a century ago, never knew the true scale of what he was pointing at. His surveys in the 1920s were not capable of resolving the structure he had detected. He knew something was there. He did not know he had found the most massive supercluster in the local universe. The Shapley Supercluster includes several individually named clusters. The most central and massive of these, the Abell 3558 cluster, sits at the heart of the concentration and is itself one of the most massive galaxy clusters known in the local universe. X-ray observations of the Shapley region show that the hot gas filling the space between galaxies within the supercluster is heated to temperatures of tens of millions of degrees by the enormous compression of matter in that region. This X-ray glow, invisible to the human eye, stretches across an area of sky larger than 1,000 full moons and reveals the true shape of the structure. But the deeper question, the one that has occupied cosmologists for the better part of 4 decades, is whether the Shapley Supercluster is the final answer to the Great Attractor mystery, or whether something beyond it is contributing to the flow. The answer, increasingly, appears to be the latter. Some peculiar velocity studies point to gravitational influences extending even beyond Shapley in directions that suggest structures at even greater distances are shaping the flow of the local universe. The universe, it seems, keeps putting up new horizons. Just when we think we have found the largest thing, something larger reveals itself. What lies beyond Shapley, and whether it connects to the rest of the structural pattern, is a question that current telescopes are only beginning to answer. Everything we have described so far, the Norma cluster, the Great Attractor, the Vela Supercluster, the Shapley concentration, all of it, is only the visible portion of a much larger structure we cannot see at all. Dark matter makes up approximately 27% of the total energy content of the universe. Ordinary matter, the kind that forms stars, planets, gas clouds, and you, makes up only about 5%. The rest is dark energy, the force driving the expansion of the universe. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we have yet detected directly. We know it exists only because of its gravitational effects, because it bends the path of light passing through it, because galaxies rotate at speeds that only make sense if far more mass is present than the visible stars and gas can account for. In the Great Attractor region, dark matter plays a crucial role. The filaments of dark matter threading through the Zone of Avoidance and connecting the clusters of the Great Attractor region form what cosmologists call the cosmic web. This web of invisible scaffolding organizes the large-scale structure of the universe, and every massive concentration of visible matter, every galaxy, every cluster, every supercluster, sits at a node where dark matter filaments intersect. Think of the cosmic web as a three-dimensional spiderweb, where the threads are dark matter filaments spanning hundreds of millions of light years, and the droplets hanging at each junction are superclusters of galaxies. The Great Attractor sits at one of the largest nodes of this web in our cosmic neighborhood. Dark matter halos surrounding the Norma cluster and its neighbors extend far beyond the visible cluster, reaching out and connecting to the dark matter scaffolding, linking them to the Shapley Supercluster in one direction and the Vela Supercluster in another. This dark matter web is what gives the structures their gravitational reach. The visible galaxies you see in images are the bright spots, but the mass doing most of the gravitational work is invisible, threading through the voids between those bright spots in long, thin filaments that carry matter from low-density regions toward high-density ones. Computer simulations of the large-scale structure of the universe reproduce this web with remarkable accuracy. The simulations, using only known physics and the measured initial conditions of the early universe, generate structures that look almost identical to what real telescope surveys find. This match between theory and observation is one of the strongest confirmations of the dark matter model we have. But here is where the story gets uncomfortable. While simulations match the overall structure well, there are some features of the local universe that do not quite fit. The extreme density of the Great Attractor region, combined with the existence of the Vela Supercluster hidden behind the zone, and the measured peculiar velocities of galaxies in this region, together create a picture that pushes the boundaries of what standard cosmological models predict. Some scientists have suggested that the local universe may sit in a region of unusually high mass concentration, a statistical outlier in the otherwise relatively uniform distribution of matter across the broader cosmos. If that is true, we are not just living in an extraordinary place. We may be living in one of the most unusual corners of the universe, and that raises questions with no comfortable answers. The universe is not static. It has never been static. From the first fraction of a second after the Big Bang, matter has been in motion, driven by gravity, by thermal pressure, by the expansion of space itself. The large-scale structure we observe today, the filaments, clusters, voids, and superclusters, is the result of nearly 14 billion years of matter organizing itself under the influence of all these forces simultaneously. The cosmic web in our neighborhood is a dynamic, evolving structure. Matter flows along dark matter filaments from voids toward nodes, from filaments toward clusters, from clusters toward superclusters. This flow has been happening for billions of years, and it will continue for billions more. In the Great Attractor region, this flow is visible. Not visible with the naked eye, but measurable through detailed surveys of galaxy velocities. When astronomers build three-dimensional velocity maps of the local universe, they can watch the flow in progress. Galaxies streaming toward the norma and Shapley concentrations like water draining toward a plug. The timescales involved in this motion are so vast that calling it dramatic feels inadequate. The galaxies flowing toward the Great Attractor today began that journey billions of years ago, accelerated gradually by gravity across a volume of space hundreds of millions of light-years wide. In the deepest surveys of the zone, astronomers have found particularly dramatic examples of this flow in action. Galaxy clusters in the outskirts of the Great Attractor region are being deformed by tidal forces, their shapes stretching in the direction of the central mass concentration. Individual galaxies within those clusters are losing their gas to ram pressure stripping as they move faster through increasingly dense intracluster gas. One of the most striking examples is the Norma cluster itself, where high-resolution X-ray observations show a tail of hot gas extending behind one of the dominant galaxies, evidence of the galaxy's headlong plunge through the cluster's atmosphere at thousands of miles per second. Meanwhile, in the voids surrounding the Great Attractor region, the opposite is happening. Dark matter and galaxies are flowing out of the voids, leaving behind increasingly empty regions of space. The largest voids in our neighborhood, including the region astronomers call the dipole repeller, are growing emptier as their matter drains toward the dense structures surrounding them. The result, on scales of hundreds of millions of light years, is a universe that looks like a slow-motion explosion that has mostly finished expanding and is now beginning to collapse locally, even as it continues to expand globally. Locally, gravity wins. The Great Attractor pulls. Matter flows toward it. Globally, dark energy wins. The universe expands. Distant galaxies accelerate away from us faster than gravity can hold them. Our cosmic neighborhood sits at the edge of this battle, in a region where local gravity is still strong enough to organize matter into massive structures, but where the long-term fate of those structures remains genuinely uncertain. What we can say is this: the Great Attractor region is not finished forming. Matter is still flowing into it. Clusters are still merging. New connections in the cosmic web are still forming. We are watching the construction of something enormous in real time, even if that real time spans billions of years. And at the heart of that construction, still partly hidden from us by the dust of our own galaxy, something is waiting. The generation of telescopes being built right now is not an incremental improvement over what came before. It is a transformation. For the past several decades, our view of the zone of avoidance has been limited by physics. Visible light is blocked by dust. Infrared penetrates partially, but not completely. Radio surveys reveal hydrogen gas, but lack the resolution to map fine structure. X-ray telescopes see the hot gas between galaxies, but need satellites with narrow fields of view. Each of these tools gave us a different piece of the puzzle. None of them gave us the whole picture. The new generation of instruments changes that. The Square Kilometre Array, currently being constructed in South Africa and Australia, will be the largest radio telescope ever built. Its total collecting area will exceed 1 square kilometre, assembled from thousands of individual antenna dishes coordinated by some of the most powerful computing systems ever built for astronomy. When fully operational, the Square Kilometre Array will be sensitive enough to detect a mobile phone signal from a planet orbiting a star 10 light-years away. In the zone of avoidance, it will map hydrogen emission from galaxies at distances and densities never before achievable, peeling back layers of the hidden universe that current radio surveys cannot penetrate. At the same time, the eRosita X-ray telescope, launched by a collaboration of German and Russian space agencies, and now mapping the entire X-ray sky with unprecedented sensitivity, is revealing the hot gas structure of the local universe in ways that complement the galaxy surveys. X-ray emission traces the hottest, densest gas in clusters and filaments of the cosmic web. By mapping this emission across the entire sky, including through the zone of avoidance where X-ray photons experience far less extinction from dust than visible light does, eRosita is building the most detailed map of the local large-scale structure ever assembled. Early eRosita results have already confirmed structures in the zone of avoidance that were previously uncertain, including parts of the Vela Supercluster at distances where radio surveys had only partial coverage. Meanwhile, the James Webb Space Telescope, operating in near-infrared and designed primarily for deep-field observations of the early universe, has already demonstrated that its sensitivity to faint infrared sources in the zone of avoidance exceeds previous instruments significantly. Upcoming surveys using the Vera Rubin Observatory in Chile will add another layer. This telescope is designed to survey the southern sky repeatedly with enormous depth and precision, building a time domain map of galaxy positions and motions across billions of light years. Together, these instruments represent a coordinated assault on the zone of avoidance. For the first time in the history of astronomy, we will have multiple high-resolution windows onto the hidden universe behind our own galaxy operating simultaneously. The discoveries that will emerge from this new data over the coming decade may rewrite our understanding of the local universe as completely as the discovery of the Great Attractor rewrote it in the 1980s. And the most intriguing possibility, the one that keeps some astronomers visibly excited in conversations about what they expect to find, is the potential for entirely new structures, perhaps as large as the Vela Supercluster, perhaps larger, sitting in the remaining 10% of the zone of avoidance that even the best current surveys cannot penetrate. Something may be waiting in that final dark strip of sky, and we are about to point instruments at it that will finally see through. Not everything in the Great Attractor region is growing. Some of the most beautiful objects in that part of the sky are in the process of being dismantled, torn apart, stripped of their substance, and transformed into something unrecognizable. Galaxy harassment, ram pressure stripping, tidal disruption, mergers. These are the processes that dominate the inner regions of the Norma cluster and its neighbors, and they are happening at a pace that, while slow on human timescales, is catastrophic on the timescale of individual galaxies. One of the most studied victims of this process is a galaxy known informally as the Jellyfish Galaxy in the Norma cluster, catalogued as ESO 137-001. X-ray observations from the Chandra X-ray Observatory revealed that this galaxy is moving through the hot gas of the cluster at millions of miles per hour, and the ram pressure of that gas is tearing its star-forming gas clouds away from the galaxy's disk. The visual effect is staggering. In X-ray images, the galaxy has a long, luminous tail of stripped material extending behind it for over 200,000 light-years. New stars are forming in this tail, born outside the main body of any galaxy, lighting up the stripped gas with blue-white stellar nurseries before the material disperses into the intergalactic medium. The galaxy itself is being starved. Its gas reservoir, the fuel needed to continue forming new stars, is being swept away by the pressure of its fall through the cluster. In a few billion years, without that fuel, the galaxy's star formation will cease. It will become a red, dead, elliptical galaxy, drifting silently through the cluster with no new stars being born in it. This transformation from a blue star-forming spiral into a red, quiescent elliptical is one of the most common outcomes for galaxies that fall into massive clusters. The cluster is not simply a gravitational trap, It is an environment that actively transforms the galaxies it captures, changing their shape, their star formation rate, and their ultimate destiny. Multiple such galaxies have been identified in the Norma cluster and its surrounding region. Some are early in the process, showing only slight distortions at their outer edges. Others are deep in transformation, their original spiral structure barely visible beneath the smeared, disrupted appearance of a galaxy under extreme tidal stress. At the very center of the cluster, where the density of galaxies is highest, two or more massive galaxies are often caught in the process of merging. Galaxy mergers are not gentle events. When two galaxies of comparable mass collide, the interaction lasts hundreds of millions of years and involves the complete restructuring of both objects. Gas clouds within each galaxy collide head-on and heat up, triggering explosive bursts of star formation. Black holes at the centers of each galaxy approach each other and eventually merge into a single, far more massive black hole. The resulting galaxy bears little resemblance to either of its precursors. In the Norma cluster's core, this process has produced some of the most massive elliptical galaxies known, cosmic giants that grew fat by consuming smaller companions over billions of years. The Great Attractor is not just pulling matter toward itself, it is processing that matter, breaking it down, rebuilding it, transforming the entire population of galaxies in its grip into a different kind of universe than the one those galaxies began in. The hidden region behind our Milky Way is not a quiet place. It is a forge for most of the history of the Great Attractor research. Astronomers focused on the pull. What is pulling our galaxy? Where is the mass? How much of it is there? These were the central questions driving the field. The assumption built into the search was that the motion of our local universe was primarily a gravitational attraction story. In 2017, that assumption was revised. A team of researchers published a detailed three-dimensional map of galaxy velocities across a vast region of the local universe, covering hundreds of millions of light-years in all directions. When they traced the flow of matter, they found something they had not fully expected to be so prominent. On the opposite side of the sky from the Great Attractor, in the direction of the constellations Perseus and Pisces, sat an enormous void, not just an ordinary underdense region of space, but a vast, low-mass region spanning hundreds of millions of light-years in which galaxies were systematically sparse. In standard cosmology, voids push matter outward toward their boundaries because the local pull of the void's interior is weaker than the pull of the denser regions surrounding it. Matter in a void falls outward toward the edges. This creates an effective repulsion, not a true force pushing matter away, but a gravitational imbalance that produces the same observable result. The team named this structure the dipole repeller. What they showed, for the first time with this level of precision, was that our galaxy's peculiar velocity, its motion relative to the background radiation of the universe, could be explained by two mechanisms acting simultaneously and with roughly comparable strength. Half the motion comes from the Great Attractor pulling our galaxy forward. The other half comes from the dipole repeller behind us, pushing our galaxy forward from the opposite direction. We are caught between two cosmic influences, one a concentration of mass so dense it bends our path through space, the other an emptiness so extreme it pushes us away from itself. The dipole repeller is not something you can point a telescope at and photograph. There is nothing to see inside it. By definition, voids are empty, or nearly so. Their existence is inferred from the absence of galaxies in surveys, from the missing mass that should be there if space were uniformly filled, and from the flow of galaxies at their edges. But the gravitational influence of the dipole repeller is real and measurable. It is baked into the velocities of thousands of galaxies across our cosmic neighborhood. This dual-engine picture of local cosmic motion has implications for how we understand the structure of the universe. It suggests that the large-scale motion of matter is shaped not just by where mass is concentrated, but also by where it is absent, by the voids that are just as much a part of the cosmic structure as the superclusters. The universe, in this view, is a system of competing pressures, densities, and voids, attractors and repellers, all working together to move matter through space along paths that no single force controls entirely. Our galaxy rides these competing currents, pulled and pushed simultaneously, heading toward a future that depends on which force ultimately dominates. And whether that future involves our galaxy merging into the heart of Laniakea, or being pulled apart by the expansion of the universe, remains one of the genuinely open questions in modern cosmology. The oldest light in the universe is a faint glow of microwave radiation that fills the entire sky uniformly in all directions. This is the cosmic microwave background, the afterglow of the Big Bang, released when the universe cooled enough for atoms to form, about 380,000 years after creation. It is the earliest snapshot we have of the universe, imprinted across the sky with tiny fluctuations in temperature that correspond to the density variations that later grew into galaxies, clusters, and superclusters. For the most part, this background radiation is extraordinarily uniform. The temperature fluctuations across the sky are tiny, roughly 1 part in 100,000, but there are anomalies. One of the most prominent and controversial is a region in the southern sky, in the direction of the constellation Eridanus, known as the cold spot. The cold spot is a region of the cosmic microwave background, roughly 13 degrees across, where the temperature is measurably colder than average. Its temperature deviation is within the range of statistical fluctuations that standard cosmology predicts, but it sits at the tail end of those expectations. It is unusually large and unusually cold simultaneously, which makes it statistically unusual enough to attract serious scientific attention. Some explanations for the cold spot are mundane. The fluctuations in the background radiation are random, and occasionally random processes produce outliers. The cold spot may simply be one such outlier, but other explanations are far more interesting. One hypothesis, supported by some observational evidence, is that the cold spot is the signature of an enormous void along the line of sight between us and the most distant background radiation. A supervoid, a region of space hundreds of millions of light years across containing far less matter than the surrounding universe, could imprint a cold signature on the background radiation as light passes through it. Photons of background radiation that travel through an expanding void lose a small amount of energy because the void is growing as they cross it. This effect, called the integrated Sachs-Wolf effect, should leave a cold imprint on the background at the location of the void. A supervoid consistent with producing the cold spot has been found by some research teams, centered at a distance of roughly 3 billion light-years, in the direction that aligns broadly with the southern sky hemisphere, toward which the Great Attractor also sits. This geographical coincidence has prompted speculation. If the local universe is already unusually dense in one direction, with the Great Attractor and Shapley Supercluster pulling matter toward the southern sky, is it possible that the local universe sits in a larger scale asymmetry of the cosmos, one that extends all the way back to the variations in the earliest moments after the Big Bang? There is no confirmed connection between the cold spot and the Great Attractor. They are separated by billions of light years and are most likely unrelated features, but the question it raises is profound. If the universe has structures even larger than superclusters shaping its overall topology, and if our region of space sits within an unusually dense concentration at multiple scales simultaneously, what does that mean for our understanding of the universe as a whole? That question does not yet have a satisfying answer. The Great Attractor does not rule the local universe alone. On the opposite side of the sky, from Norma and Centaurus, in the direction of the constellations Perseus and Pisces, sits one of the most massive concentrations of matter in our cosmic neighborhood. The Perseus-Pisces supercluster stretches across roughly 300 million light-years and contains dozens of galaxy clusters embedded in a long, curved filament of matter that traces one of the major structural features of the local cosmic web. The Perseus-Pisces supercluster includes the Perseus cluster, which is one of the most studied galaxy clusters in the sky. At the center of the Perseus cluster sits one of the most massive single galaxies known, a giant elliptical called NGC 1275, which has consumed scores of smaller galaxies over its multi-billion-year history and grown into an object visible in small amateur telescopes from Earth. But Perseus-Pisces is more than just a collection of impressive objects. It is a gravitational counterweight. While the Great Attractor region pulls our galaxy and the rest of the local group toward the south, the Perseus-Pisces supercluster pulls in the opposite direction, toward the north. These two concentrations of matter sit on roughly opposite sides of our location in the universe, creating a gravitational tension that shapes the flow of matter through the entire local volume. The net motion of our galaxy, the direction we are actually moving, is the result of adding together all these competing pulls and pushes. The Great Attractor pulls. The Shapley Supercluster reinforces that pull. The Vela Supercluster adds its contribution. The dipole repeller pushes from the back. Perseus-Pisces pulls from the other side. The resulting motion is a vector, a specific direction and speed that points toward the southern sky, but does not point exactly at any single one of these structures. It is a compromise motion, the galaxy's response to all the competing forces simultaneously. Understanding this multi-force picture required decades of increasingly precise measurements of galaxy velocities across the local universe. Early surveys in the 1980s and 90s could identify the general direction of the flow, but not decompose it into individual contributions. By the 2010s, improved surveys covered enough volume with enough precision to start separating the effects. The picture that has emerged is of a local universe in a complex, dynamical state, caught between multiple large-scale structures pulling it in different directions, with the Great Attractor and Shapley dominant, but not the only players. For our galaxy specifically, the question of its long-term future depends on which of these forces ultimately wins out. In the short term, cosmologically speaking, the expansion of the universe is accelerating, driven by dark energy. This expansion is working against all the gravitational attractions, slowly pulling everything apart. In the intermediate future, our local group of galaxies will merge. The Milky Way and Andromeda are already on a collision course. In roughly 4 billion years, they will begin their merger, eventually producing a single large elliptical galaxy. After that, on timescales of hundreds of billions of years, the expanding universe will have pulled most other galaxies beyond the range where gravity can reach them. Whether our merged galaxy will have by then fallen into the Great Attractor or will remain isolated as the universe continues to expand depends on physics we are still working to fully measure. The rivalry between Perseus-Pisces and the Great Attractor may never be resolved. The universe may end its accessible history before either force wins. Before the new telescopes arrive, before the square-kilometer array comes fully online, before the next generation of surveys begins, astronomers are already running experiments, not physical experiments, computational ones. The largest cosmological simulations ever run use the same basic physics the universe uses: gravity, dark matter dynamics, gas pressure, radiation, and the expansion of space, and simulate the evolution of a virtual universe from just after the Big Bang to the present day, across volumes of space containing billions of galaxies. The most relevant of these simulations for understanding the Great Attractor mystery are what scientists call constrained simulations. Unlike unconstrained runs that simply start with random initial conditions and let the physics play out, constrained simulations are seeded with data from real surveys of the local universe. The initial conditions are tuned to reproduce the large-scale structure we actually observe, and then the simulation runs forward in time to see whether the final state matches the observed universe in detail. The illustrious TNG simulation, one of the most powerful ever run, models a cube of the universe roughly 1 billion light-years across, tracking the evolution of approximately 3 billion particles representing dark matter and ordinary matter. When researchers run versions of this simulation constrained to match the general features of our local universe, they consistently reproduce structures that look like the Great Attractor region. Dense nodes form where multiple dark matter filaments intersect. Galaxy clusters grow at these nodes by accreting surrounding matter. Large-scale velocity flows develop, with matter streaming toward the densest concentrations. The simulations have been particularly useful for exploring the zone of avoidance. Because simulations are not limited by the dust of the Milky Way, researchers can examine what their virtual universe looks like in the direction equivalent to our own zone of avoidance, without any obstruction. What they find there is consistent with observations. Dense structures, analogues to the Norma cluster and the Vela Supercluster, form preferentially in regions where the initial density fluctuations were strongest. The distribution of mass in that region of the simulated universe agrees well with what limited surveys of the real zone of avoidance have revealed, but the simulations also reveal things we have not yet confirmed observationally. They suggest that the full mass concentration in the Great Attractor region is likely larger and extends over a greater volume than current surveys can confirm, because portions of it remain hidden in the densest parts of the zone of avoidance. They also suggest that the connection between the Great Attractor region and the Shapley Supercluster is not merely a loose gravitational association. The two structures are linked by a massive dark matter filament that channels matter from one to the other, a cosmic bridge of invisible mass spanning hundreds of millions of light years. This dark matter bridge has not been directly detected, but its existence is implied by the simulations and is consistent with the measured velocity flows in that region. If real, it would make the Great Attractor and Shapley Supercluster not two separate structures, but two peaks in a single extended mass concentration, the largest coherent structure in the local universe. The final mapping of that structure, if it exists as the simulations suggest, is a discovery waiting to happen, and it may be hiding, in part, behind the dust of our own galaxy. Numbers in astronomy are often so large that they become abstract, stripping away their power to actually communicate anything meaningful. So let us try something different. Our solar system orbits the center of the Milky Way at roughly 515,000 miles per hour. That is fast enough to circle Earth in about 3 minutes. But that is just the orbital speed. It does not capture the motion of the whole galaxy. The Milky Way itself moves relative to the cosmic microwave background at approximately 1,300,000 miles per hour. That is the combined result of all the gravitational forces we have been discussing. The pull of the Great Attractor, the push of the dipole repeller, the counterpull of Perseus Pisces, and the contribution of dozens of smaller structures. 1,300,000 miles per hour. In 24 hours, our galaxy moves about 31 million miles from where it was. In 1 year, it travels roughly 11 billion miles through space relative to the background universe. These distances are still small compared to the size of the local universe. At the current speed, it would take our galaxy hundreds of billions of years to cross the distance to the Great Attractor on its own. But our speed is not fixed. As we get closer to the mass concentration, gravity pulls harder and the speed increases. What is also worth noting is that this motion is not smooth and uninterrupted. As our galaxy falls through the local universe, it encounters the gravitational fields of other mass concentrations, which deflect its path. The Virgo cluster, sitting about 54 million light-years away, exerts a small but real gravitational pull that slightly modifies our trajectory. The local group's own internal dynamics add perturbations. The path our galaxy traces through space is not a straight line. It is a curved, complex trajectory shaped by every mass concentration in the local universe, a trajectory that takes billions of years to complete any recognizable arc. Understanding this trajectory precisely is one of the goals of the next generation of peculiar velocity surveys. with thousands rather than hundreds of galaxy velocities mapped to high precision, the gravitational potential of the local universe can be reconstructed in much finer detail, allowing astronomers to effectively trace our path backward in time and forward into the future. What those future trajectories show depends heavily on whether we have found all the major mass concentrations contributing to the flow. The discovery of the Vela Supercluster in 2017 changed the calculations. The possibility of additional undiscovered structures in the Zone of Avoidance changes them further. Every new structure found in the hidden region behind our galaxy slightly adjusts the predicted trajectory of everything in the local universe. We are navigating by a map that is still being drawn. The cartographers working on that map are using instruments we have described in earlier parts of this story: infrared surveys, radio telescopes, X-ray satellites, and computational simulations. What they will find in the final, unexplored patches of the Zone of Avoidance will determine whether we have found the largest structures shaping our cosmic trajectory, or whether there are still giants hiding in the dark that no one has measured yet. The speed of our galaxy tells us something enormous is out there. We just have not seen all of it. When all the surveys are combined and all the models are run, the question that sits at the center of this story is the simplest and most difficult one. What exactly is at the gravitational heart of the Great Attractor? The answer, as of now, is complicated. The center of the gravitational basin of the Great Attractor region, the point toward which all the surrounding matter is flowing, sits in the Zone of Avoidance. Specifically, it sits in a part of the zone where multiple dense structures overlap and where the dust of the Milky Way makes definitive identification of individual structures difficult, even with the best current instruments. The Norma cluster is the most massive single object near the center that has been confirmed, but the cluster is embedded in a larger concentration of galaxies that extends over many millions of light years and includes dozens of smaller clusters, galaxy groups, and individual galaxies flowing together in a complex, three-dimensional structure. This broader concentration is sometimes called the Great Attractor Supercluster, though astronomers prefer more precise descriptive terms because the boundaries of the structure are still not sharply defined. What is clear is that the center of gravitational attraction sits within this broad concentration, and that its exact location is still uncertain within a range of tens of millions of light years. The challenge is similar to trying to find the exact center of a cloud. You can identify where the cloud is densest, but the gradual transition from cloud to clear sky does not have a single definitive boundary. Radio surveys have identified several galaxy cluster candidates in the densest part of the Zone of Avoidance that may be significant contributors to the central mass concentration. Some of these are only partially characterized, with distances estimated from their radio properties rather than from optical spectroscopy, because their optical counterparts are too obscured by dust to obtain reliable measurements. One cluster in particular, identified in radio surveys and given the designation PKS 1656+053, has properties suggesting it may be a massive cluster sitting close to the gravitational center of the attractor region. But confirming its distance and mass requires observations in a wavelength band that can penetrate the dust, and those observations are still in progress. This is the frontier of the field. Not the well-studied clusters that have been in textbooks for 30 years, but the half-characterized objects sitting in the thickest part of the forbidden zone, waiting for the right instrument to pin them down. The researchers working on this problem operate in a kind of permanent scientific suspense. Each new survey reveals new objects. Each new object requires follow-up observations to characterize. Each characterization reveals new questions about how the object fits into the broader picture. The center of the Great Attractor may never be pinpointed to a single object. It may turn out to be a diffuse concentration of mass without any single dominant cluster, a gravitational heart made of many equally important parts rather than one overwhelming anchor. Or the final surveys may reveal something specific and unexpected. A cluster so massive, it changes the picture entirely. A dark matter concentration with no visible counterpart, a structure that does not fit any current model. The universe has surprised us before when we finally looked carefully in a direction we had been avoiding, and it may do so again. Imagine two massive whirlpools in the ocean, separated by a few miles of water. Each whirlpool pulls in currents from its surroundings. Each shapes the flow of water across a wide area. And each, over time, attracts the water that the other is drawing toward it, because the current flowing toward one whirlpool eventually passes close enough to the other to feel its pull as well. Now, replace whirlpools with superclusters, replace ocean water with dark matter and galaxies, replace miles with hundreds of millions of light years, and you have a rough analogy for the relationship between the Great Attractor region and the Shapley Supercluster. These two enormous concentrations of mass sit in roughly the same direction from our galaxy, separated by several 100 million light years. The Great Attractor region is closer, Shapley is further away, but significantly more massive. Both are pulling on the local universe. Both are drawing matter toward themselves. And the question cosmologists have been asking for decades is whether their combined gravitational influence will eventually bring them together, merging them into a single, even more massive structure. The answer depends on a race between two forces. Gravity works to pull them together. The expansion of the universe works to drive them apart. Which force wins determines the fate of the two superclusters. Current estimates of the masses of the Great Attractor region and the Shapley Supercluster, combined with measurements of the expansion rate of the universe, suggest that the outcome is genuinely uncertain. Both structures are massive enough to be gravitationally bound locally, meaning the galaxies within each supercluster will continue falling toward their respective centers rather than dispersing into the expanding universe. But whether the two superclusters themselves are bound to each other, whether gravity across the hundreds of millions of light years separating them is strong enough to overcome the expansion of space between them, is a harder question. Some calculations suggest that the Great Attractor region and Shapley are members of the same larger gravitationally bound structure, the infall regions of which overlap. In this view, the combined system will eventually merge over cosmological timescales, producing a single enormous concentration of mass far larger than either structure is today. Other calculations suggest that the accelerating expansion of the universe will prevent this merger. The rate at which space is expanding between the two structures is increasing, driven by dark energy, and may outpace the gravitational pull that would otherwise draw them together. The resolution of this question requires more precise measurements of both the masses of these structures and the rate of cosmic expansion, measurements that are actively being refined by current and future surveys. What we can say is that within Laniakea, our own cosmic home, the flow of matter toward the Great Attractor region will continue. Our galaxy and the thousands of others in our supercluster will keep falling toward that gravitational core. Whether that core will eventually merge with Shapley into a larger complex, or whether the two giants will remain separate entities drifting apart as the universe expands, is a question the universe itself has not yet decided. The answer may depend on physics, specifically the nature of dark energy, that we do not yet fully understand. And that uncertainty, the honest admission that some of the most important questions about our cosmic future remain genuinely open, is what makes this one of the most exciting times to be studying the universe. Here is a question that does not yet have a satisfying answer. If we add up all the mass we have identified in the Great Attractor region, the Norma cluster, its surrounding supercluster, the Vela Supercluster discovered in 2017, and the contribution of the Shapley Supercluster, do we fully account for the observed motion of our local universe? Some recent analyses suggest that the answer is no. Not by a small margin. The discrepancy, in certain studies, is significant enough to imply that there may be additional mass concentrations beyond Shapley at even greater distances, contributing to the large-scale flow of matter in our region of the universe. This is a deeply unsettling possibility, because Shapley is already extraordinarily far away and extraordinarily massive. The idea that there could be structures beyond it exerting measurable gravitational influence on matter hundreds of millions of light-years closer adds a new layer of strangeness to the picture. Some peculiar velocity surveys have reported hints of a broader flow field, sometimes called the bulk flow, that extends across a volume larger than Laniakea and points in the same general direction as the Great Attractor. If this bulk flow is real and accurately measured, it implies that the gravitational source driving it extends beyond Shapley to distances approaching 3 billion light-years. What structure could sit at 3 billion light-years and produce a measurable gravitational signal across such a distance? No specific supercluster has been identified at that distance that would be large enough to account for the effect. The candidate would have to be either an unusually dense concentration of matter or an anomaly in the distribution of dark matter at scales larger than any supercluster ever detected. Some researchers have proposed that the bulk flow signal, if confirmed, could be evidence for what they tentatively call a Shapley concentration extension, a broader region of enhanced density that extends well beyond the catalogued boundaries of the Shapley Supercluster and includes multiple massive clusters not previously recognized as part of a single connected structure. This remains speculative. The bulk flow measurements themselves are debated, with different surveys using different galaxy samples finding different results. The discrepancies between surveys may reflect systematic errors in the measurements rather than a true anomaly in the underlying physics. But if the bulk flow is real, and if it requires a gravitational source beyond Shapley to explain it, then our map of the local universe is still incomplete in a fundamental way. We would be in the position of someone who has identified the major rivers on a continent but has not yet found the ocean that feeds them all. The ocean, in this analogy, would be a structure larger than Shapley sitting in the background, shaping the flow of matter across billions of light-years through its sheer gravitational presence. Whether such a structure exists is a question that current observations cannot definitively answer. It will require the next generation of surveys covering larger volumes of the universe with greater sensitivity and precision than anything yet attempted. The answer may come within the next decade as the Square Kilometre Array and the Vera Rubin Observatory come online and begin mapping the local universe in unprecedented detail. Or the answer may be that the bulk flow is a statistical artifact and the map is complete. But the possibility that something even larger than Shapley is hiding in the deep background, pulling at our cosmic neighborhood from a distance of billions of light-years, is not zero, and that is enough to keep the question alive. None of what we have described will affect your life today, or tomorrow, or during the lifetime of anyone alive on Earth right now. The forces shaping the cosmic motion of our galaxy operate on timescales measured in billions of years. The Great Attractor is 250 million light-years away. Even at our current speed of over 1 million miles per hour, it would take our galaxy more than the current age of the universe to travel that far. But the question of what this ultimately means for Earth, for life, for whatever comes after us, is not entirely disconnected from the story we have been telling. Over the next 4 billion years, the Milky Way and Andromeda will collide and merge. This merger will rearrange the positions of stars, potentially disrupting the outer reaches of the solar system, but almost certainly leaving Earth's orbit intact, since the space between stars in a galaxy is so vast that direct stellar collisions are essentially impossible during a galaxy merger. After the merger, the combined galaxy will settle into a large elliptical shape, its star formation gradually declining as the gas supply is consumed. Beyond that, on timescales of tens to hundreds of billions of years, the expanding universe will isolate our galaxy from all others except those already gravitationally bound to us. The cosmic web will thin. The flows we have described will slow as dark energy accelerates the expansion beyond the point where gravity can maintain them. Trillions of years from now, the last stars will exhaust their fuel and burn out. The universe will grow dark, None of this is within any human timescale of concern. But understanding our place in the cosmic web, knowing that our galaxy is part of an enormous structure flowing toward a gravitational center hidden behind our own dust, knowing that there are structures on scales that dwarf everything we can see, and that our movements through space are shaped by forces operating on unimaginable scales, this changes something about how we understand ourselves. We are not stationary. We are not central. We are not isolated. We are part of a flow that began billions of years ago and will continue for billions more. We live on a small planet orbiting an ordinary star inside a galaxy that is falling through space in a direction we spent most of human history unable to see. The Great Attractor and everything behind it in the Zone of Avoidance is not just a scientific curiosity, it is the context for our existence. It is the gravitational landscape we inhabit, the cosmic terrain we are passing through at speeds that would seem impossible on any human scale. Understanding that terrain is not separable from understanding who and what we are in the universe. And the most honest thing we can say, after decades of brilliant scientific work, is that we have learned a great deal and still do not see the complete picture. Something massive is hiding behind the Milky Way. We have found parts of it. We have named some of the pieces. We have measured the pull, but the hidden zone still guards its secrets. The new telescopes are pointed. The surveys are beginning. And whatever is revealed in the coming years will again expand the boundaries of the largest thing we know. Radio waves are patient. They travel at the speed of light through dust, through gas, through the entire thickness of the Milky Way, without losing their direction. They carry information from objects so distant that the light we use to see them would never reach us at all, swallowed by the very galaxy we live inside. In the decades since radio astronomy opened this hidden window, some of the most intriguing signals received from the Zone of Avoidance have come from active galactic nuclei, the violently energetic cores of galaxies where supermassive black holes are actively consuming material and launching jets of plasma into space at nearly the speed of light. These jets emit radio waves so powerfully that they can be detected across hundreds of millions of light years. A radio-bright active galaxy in the Zone of Avoidance can be identified from its signal alone, long before any optical or infrared counterpart is located or confirmed. One such source, identified in radio surveys of the Zone of Avoidance in the 1980s, sits close to the gravitational center of the Great Attractor region. Its radio brightness suggests a massive, active galaxy at the heart of a dense cluster environment, where the galaxy's central black hole is being fed by material stripped from neighboring galaxies in frequent collisions. This object has been studied in infrared and radio wavelengths, but its full character remains partially obscured by dust. It sits in the densest part of the forbidden zone, where even infrared surveys have difficulty separating individual sources from the background confusion. Other radio sources in the Zone of Avoidance have been similarly intriguing. A survey conducted with the Parkes telescope in the late 1990s identified a population of galaxies in the zone that appeared to be concentrated in a way inconsistent with random distribution. Their clustering suggested a mass concentration in the background, an additional component to the Great Attractor that had not been mapped in galaxy surveys. Some of these radio-identified galaxies have since been confirmed as members of clusters associated with the Norma cluster complex or the extended Great Attractor region. Others remain unclassified, their distances uncertain, their masses unmeasured, sitting in catalogues as unresolved clues to the structure of the hidden universe. The completeness of the radio catalogue of the Zone of Avoidance has improved dramatically over the past 20 years with deeper surveys and improved data processing. But the definitive characterization of all radio sources in the zone, matching each one to its host galaxy and placing it accurately in three-dimensional space, remains a work in progress. The signals we have received tell us something is there. They tell us it is massive, active, and gravitationally organized. They do not yet tell us the full extent of what we are looking at. when the square-kilometre array begins its all-sky survey with sensitivity exceeding current instruments by orders of magnitude, the radio picture of the zone of avoidance will transform almost overnight. Objects that currently appear as faint, unresolved sources will be resolved into individual galaxies with measured velocities. Clusters that are currently catalogue entries will become three-dimensional structures with known masses. The oldest signals from the hidden sky are telling us something. The instruments we need to fully translate them are almost ready. What those signals have been saying, across decades of patient observation, is that the universe behind our galaxy is far more structured, far more massive, and far more dynamic than any map we have drawn so far. One of the most basic assumptions of modern cosmology is that the universe does not have a center. The Big Bang did not happen at a point in space. It happened everywhere simultaneously. Every location in the universe is equally valid as a reference point. The universe looks roughly the same in all directions when averaged across large enough scales. This is called the cosmological principle, and it is the foundation on which most of our understanding of the large-scale universe is built. But the existence of the Great Attractor, the Zone of Avoidance, the Laniakea Supercluster, and the flow of matter across hundreds of millions of light-years in a specific direction raises a question that is worth sitting with. Are we actually observing the cosmological principle being violated? Is the local universe genuinely different in different directions in ways that go beyond statistical fluctuation? The short answer is that what we are observing is consistent with the cosmological principle when viewed at large enough scales. Superclusters exist in all directions. Dense regions and voids are distributed throughout the observable universe. The cosmic web is a global structure, not a local anomaly. But there is a longer answer that is less comfortable. When we average the universe over scales of a few 100 million light-years, the kind of scale relevant to our local cosmic neighborhood, the distribution of matter is not uniform. Our local universe is genuinely unusual. The combination of the Laniakea Supercluster, the Shapley concentration, the Vela Supercluster, and the other massive structures we have described makes our corner of the cosmos one of the denser, more organized regions of the observable universe. Whether this is a rare statistical fluctuation, an outlier within an otherwise uniform distribution, or evidence of something more fundamentally unusual about our location is a question that current observations cannot definitively answer. The cosmological principle is an assumption about the universe at very large scales. Our local region deviates from uniformity at the scales we have been discussing, and that deviation is real and measurable. Some cosmologists have proposed that the observable universe may contain structures even larger than the cosmic web, which, if real, would represent significant challenges to the standard cosmological model. These proposals are speculative and controversial. They require observations across volumes of the universe far larger than what has been comprehensively surveyed. Current evidence neither confirms nor definitively rules them out, but they point to an underlying tension in the field. The more precisely we measure the local universe, the more organized and structured it appears. And the more structured it appears, the more it pushes against the assumption that the universe looks the same everywhere. If we are not at the center of the universe, which we almost certainly are not in any fundamental sense, we may nonetheless be living in an unusually organized region of it. A pocket of the universe where the cosmic web is particularly dense, where superclusters are particularly massive, where the flows of matter are particularly dramatic. That would mean the night sky we observe from Earth, the galaxies we have catalogued, the structures we have discovered behind the zone of avoidance, are a skewed sample of the universe as a whole, a sample that shows us one of the most extraordinary corners of the cosmos. And behind the dust of the Milky Way, in the region we could not see for most of our history, the most dramatic parts of that extraordinary corner are still being revealed. The universe does not have a center, but it is becoming clear that we may be living very close to something that functions like one. 10%. That is the fraction of the zone of avoidance that remains genuinely opaque to current instruments, not difficult to see through. not partially obscured, completely blocked by the densest accumulations of gas and dust in the Milky Way, most of them concentrated near the galactic center itself. This 10% of the sky is not uniformly distributed. It forms a narrow strip along the galactic plane, thickest toward the center of the galaxy in the direction of the constellation Sagittarius, and thinning toward the outer galactic regions. Within this 10% lies the galactic center itself, the region surrounding the supermassive black hole at the heart of our galaxy, which sits 4 million times the mass of our own star. The galactic center environment is one of the most extreme in the Milky Way, with dense gas clouds, young star clusters, and high-energy radiation filling the space around the central black hole. Observations of the galactic center use radio waves and high-energy X-rays and gamma rays, which penetrate the dense material that blocks visible and infrared light. These observations have revealed the galactic center in extraordinary detail, mapping its structure to within light hours of the central black hole. But for studies of galaxies behind the galactic center, these same observational techniques are much less useful. Radio observations can detect hydrogen emission from background galaxies, but the radio sky near the galactic center is crowded with sources from within our own galaxy, making it extremely difficult to identify individual background galaxies against the confusion. This is the final frontier of the Zone of Avoidance, and within it, structures of unknown size and mass may be hiding in plain sight. The current best constraint on what lies behind the galactic center comes from a combination of radio surveys and computer simulations. The simulations suggest that the mass distribution behind this hidden strip should be broadly similar to what has been found in the more accessible parts of the zone, a continuation of the large-scale structure visible on either side of the opaque strip. But simulations are not measurements. They can tell us what the physics predicts. They cannot tell us what is actually there. Several research groups are pursuing strategies to push observations further into this final opaque strip. One approach uses the technique of gravitational lensing, in which massive foreground objects in our own galaxy bend and amplify the light from background galaxies, making them momentarily visible even through otherwise opaque dust. Another approach uses longer wavelength radio observations, where the 21-centimeter hydrogen line remains detectable even through the densest molecular clouds in the galactic center region. A third approach relies on the X-ray sensitivity of next-generation space telescopes, which may be able to detect the X-ray glow of hot gas in massive clusters behind the galactic center even when the optical counterpart is completely invisible. None of these techniques has yet produced a definitive discovery in the deepest part of the hidden zone, but the sensitivity of instruments in all these wavelength bands is improving steadily. The 10% that remains hidden is shrinking, not quickly, not dramatically, but steadily, with each new survey, with each new instrument, with each new technique. What it contains, whether more clusters like Norma, additional structures like Vela, or something entirely unexpected, is not yet known. That is the honest answer, and it is one of the most exciting sentences in modern science. We have traveled far in this story, from the first astronomers who noticed the Zone of Avoidance and admitted they could not see through it, to the radio surveys that first detected galaxies on the other side, to the infrared missions that opened a window into the hidden universe, to the discovery of the Norma cluster, the Great Attractor, the Vela Supercluster, and the hints of something even larger beyond Shapley. We have traced the motion of our galaxy at over 1 million miles per hour, felt the dual pull of the attractor and the push of the dipole repeller, and discovered that our cosmic home, Laniakea, spans 500 million light-years and is still flowing toward its gravitational heart. What does it all mean? It means we live in an extraordinary place, not at the center of anything, not privileged in any cosmic sense, but located in one of the most dynamically complex and gravitationally rich corners of the observable universe. Our galaxy is participating in a flow of matter that has been underway for billions of years, pulled by invisible forces towards structures that were unknown to science until the last 50 years. The Zone of Avoidance, the region that once represented the limits of our knowledge, has become the frontier of our discovery. Every instrument we point at it reveals more of what was always there, waiting to be seen. The Great Attractor is real. It is a concentration of mass spanning tens of millions of light years, anchored by the Norma cluster, extended by surrounding superclusters, reinforced by the Shapley concentration, complemented by the Vela Supercluster, and possibly connected to structures we have not yet mapped at all. Our galaxy is not heading toward a cliff. It is heading toward a denser, more complex, more ancient part of the universe than the region it currently occupies. A region that has been assembling itself for nearly the entire age of the cosmos. And yet, despite everything we have learned, the most important sentence in this story may be this one: we have not finished the map. The Zone of Avoidance still hides 10% of the sky completely. The surveys needed to characterize its hidden structures are still being built. The simulations that predict what is there have not been fully tested against direct observations. The bulk flow that may indicate structures beyond Shapley has not been definitively confirmed or ruled out. The universe behind our galaxy is still giving up its secrets. Slowly, one survey, one discovery, one recalculated trajectory at a time. What we know with certainty is this: something massive is hiding behind the Milky Way. It has been pulling on our galaxy and millions of others for billions of years. It is getting no closer to us in any human sense, but in the cosmic sense, we are falling toward it inexorably at speeds that make any rocket ever built look stationary, and we are watching it with better eyes than any generation before us. The next discoveries will not come from speculation or imagination. They will come from the data. From the signals arriving every night at dishes in South Africa and Australia, from the X-ray photons being collected in orbit, from the infrared images being processed in computer clusters around the world, the pull we cannot escape has become the mystery we cannot stop chasing, and the chase is far from over.